It has been over 5 decades since humans last operated on the lunar surface. The year was 1970. That half-century gap represents more than a pause in exploration. It reflects the loss of the specialized manufacturing and flight-proven experience required to survive beyond low Earth orbit. Now, in the spring of 2026, a new launch window has finally opened. Tomorrow, April 1st, at precisely 1830, the vehicle is scheduled to leave the pad. While the Apollo missions targeted the surface, this profile is strictly limited to deep space vehicle verification. There will be no landing attempt. This schematic illustrates the trajectory. The vehicle travels outbound, looping around the moon's far side. Utilizing a free return trajectory, it uses lunar gravity as a slingshot, setting a continuous path back to Earth without a second engine ignition. Because no descent sequence is programmed, the success of the mission rests entirely on the vehicle's ability to maintain life support and maintain structural integrity in deep space. Reaching this launch window took over a decade of development, defined by a history of sudden cancellations and rescheduled windows. These cancellations occurred because the hardware repeatedly reached the physical boundary limits of its design. The path from the program's inception in 2011 to this April window was gated by thermal system failures and fluid dynamics anomalies. In human-rated flight, a delay is the final safety mechanism in action. Each scrub proves the automated systems are identifying and halting at deviations that would otherwise result in vehicle loss. The program finalized its initial system architecture in 2011. Initial internal projections targeted 2019 for the first major integrated flight test. 2019 passed without a vehicle reaching a state of flight readiness. The secondary schedule slip saw the 2020 launch date arrive and depart without an ignition sequence. These early phase delays between 2011 and 2020 were macro-level developmental and logistical roadblocks, typical of large-scale aerospace integration. By 2023, the program transitioned into the active launch readiness phase, where software and hardware are tested under flight-simulated conditions. In 2023, the first major hardware-level gating event occurred. Engineers identified severe issues with the thermal protection tiling on the exterior of the capsule. Post-test inspections showed that the heat shield material was burning and shedding in an irregular, unmodeled pattern. A heat shield functions through ablation, the engineered controlled charring and shedding of material to carry thermal energy away from the hull. As the capsule enters at circumlunar velocities, it generates a massive bow shock wave. This CFD model shows predictable ablation dissipating heat safely. But if unpredictable, the shield develops thin spots. Thermal energy breaches the barrier, compromising the structure and crew. A subsequent attempt in September 2025 was also halted when system constraints during a wet dress rehearsal revealed further hardware anomalies. The shift from scheduling slips to acute thermal degradation confirms the program moved into a phase where uncompromising physics dictates the timeline. Which brings us to the current year, 2026. The vehicle is on the pad, fully integrated and undergoing the final terminal count. The first attempt this year occurred on February 8th. As the clocks ticked down, sensors identified a liquid hydrogen anomaly within the core stage tanks. Liquid hydrogen is uniquely difficult to manage. As the smallest molecule in the universe, it can migrate through microscopic imperfections in metallic seals. To maintain its liquid, combustible state, the hydrogen must be kept at extreme cryogenic temperatures, near absolute zero. When a seal fails under pressure, the result is a violent blast of superchilled vapor. Because hydrogen is highly flammable, any leak near the ignition source of the engines creates an uncontainable combustion hazard. The February 8th launch was immediately scrubbed. Engineers replaced the seals and recycled the countdown for February 21st. This second attempt was halted by a different fluid dynamics failure, an irregularity in the helium pressurization system. Helium is used as a pressurant gas. It does not ignite. Instead, it provides the physical force needed to move propellants through the vehicle's plumbing. This schematic shows the operation. Helium forcefully pushes liquid propellants into combustion chambers at constant pressure. On February 21st, irregular helium flow caused downward pressure to stutter. Fuel delivery became inconsistent, causing a total loss of thrust during ascent. A single micro-component failure in gas routing renders a multi-billion-dollar vehicle unlaunchable. Pulling back from individual valves and heat shields reveals the broader architecture of this mission. The history of Artemis is a record of these physical gates: 2011, 2019, 2020, 2023, September 2025, and the 2 attempts in February 2026. Each date on this timeline represents a specific subsystem that enforced a safety gate on the mission. A terminal countdown functions as a dynamic safety test, verifying every subsystem under actual operational loads before commitment to flight. As of this morning, the agency has cleared all previous technical hurdles and verified readiness for the April 1st window. The clocks are now ticking toward the 1830 ignition target. Success tomorrow depends on whether the thermal and cryogenic systems can maintain their exact mathematical tolerances once the engines ignite. This decade of data and testing raises the question: has the engineering finally reached the level of reliability required for a lunar return? Based on the sequence of failures and fixes analyzed, what is your prediction for tomorrow's countdown? The intellectual challenge of spaceflight is found in the rigorous, uncompromising physics of the countdown itself.